Obviously, I'm going to talk to you about STEC. For those of you, which I think is quite a lot, who've been here over the last couple of months, there's a decent chance that at some point Michael grabbed you, pulled you in front of a laptop and showed you things. So you might already know a bunch of that. If not, I'm now going to tell you. And the nice thing about giving the second talk in a workshop is that I can start by saying a bunch of obvious things which haven't been said yet and somebody has to. And it's nice because that allows me to spin things in the direction that I want to. We all know what the point of formal mathematics is, i.e. it allows us to do automated or interactive theorem proving and like verifying proofs. And if we extend the notion of formal mathematics to things like computer algebra system, then we can even do computation things, we can do things like semantic search, all of these kinds of things. That, of course, only works because we're able to unambiguously represent mathematical statements in the first place, which is both a requirement for doing all the nice things in the first bullet points, but I would argue it's also an intrinsic good in its own. And the way that that works is, of course, by providing some kind of unique identifier scheme for semantically distinct symbols, which means we can actually refer to exactly the thing that we want in an unambiguous manner, which is nice. And then we can collect those in libraries, and we can share these libraries and work on them communally and collaboratively, depending on the language, occasionally modularly. Yeah. So all of these nice things that formal mathematics has, especially in comparison to informal mathematics. The flip side of that is, of course, we need like specialized tools and dedicated languages, which are generally difficult to learn, especially for those of you who are not, for whom learning formal syntax is not second nature anyway. There are multiple more or less competing systems and languages of which you have to choose. Knowledge does not necessarily transfer to them in a direct way. You have to be very detailed in all of the things that you need to describe. The syntax ultimately looks ugly from the point of view of like an informal mathematician. All of these kinds of things, which is ultimately just an elaborate and convoluted way to think that the point of formal mathematics is to communicate mathematical ideas to a computer. And most of the drawbacks that come with that are just natural and necessarily prerequisites of exactly that. Comparing that to informal mathematics, the TLDR again is obviously here the point is to communicate mathematical ideas to other human beings. And that gives us a lot more flexibility. First and foremost, we can actually use natural language, which is nice. We don't have to learn a formal one. The flip side of that, of course, it might be the wrong natural language. We have a whole bunch of notations and terminology that has evolved through cultural evolution over centuries to be concise, expressive, and quote-unquote unambiguous. They're not actually unambiguous in practice. But usually by context you mean, you know what they're trying to mean. We can focus on the actual ideas because that is what matters to other human beings rather than having to like deal with boring and irrelevant details. Occasionally even at the cost of technical formal consistency. To just give a few examples, Michael recently sent me this introductory script to mathematics for computer scientists or whatever for flexi-formalizing. And they do this quite popular thing where they basically start with naive set theory. Then at some point they mention that Russell's paradox exists and vaguely hand wave in the direction of axiomatic set theories and then just continue with naive set theory because that's perfectly fine. And computer scientists in their first semester don't need to care about the other details. Generally, unrestricted comprehension shows up a lot. If you do things like set theoretic forcing, you will likely read these phrases with, here we use a countable transitive model of CFC, where technically, of course, they mean a countable transitive model of some finite subset of CFC containing exactly those instances of the axiom schemas that we need for all the stuff that comes afterwards. Take that with a grain of salt. It's been a while. I might be saying nonsense, but you know these kinds of situations. We like often in informal mathematics write things that is technically not correct and might even be inconsistent, but we all know that there is a way to make that correct and therefore it's okay. And it allows us to focus on the stuff that we actually want to communicate, which is usually the idea behind a proof or the intuition behind the definition, these kinds of things. Also, generally, it doesn't matter what you think the real numbers are, for example, whether they're like leading cuts or whatever. We all know what the real numbers are, therefore I can just leave that unspecified. I don't need to bother with formal foundations, whether that is set theory or dependent type theories or whatever. Informal mathematics has a lot of narrative stuff that formal systems don't care about at all because they're not relevant for their purposes. Things like examples, exercises, remarks, intuitions, various kinds of paragraphs, explaining what the point of whatever we're currently doing is, foreshadowing, recapping, all these kinds of things. And unlike formal system, informal mathematics actually does have a standard system for better or worse, which is LaTeX. For better, because at least there is one. For worse, because it's software from the 70s and we desperately need something better and it's not going to happen. The drawback, of course, is ultimately it's computationally opaque. We can't really do much with it from the point of view of software support, except for LaTeX, I guess. And of course, things are ultimately ambiguous everywhere. Apart from context, which you may or may not have as a more or less informed reader of such a text. I'm guessing most of you don't actually need to see the slide, but I made it a couple of years of it and I like it, therefore I'm going to show it, which is this comparison of basically the same statement in informal math, which is nice and pretty and what it's supposed to look like, and then this mess of formal syntax, which you may or may not be able to read in some instances and not at all in others. Yeah. Also, by the way, note that the word triangle occurs nowhere in the formal parts. I mean, it doesn't have to, obviously, but it's kind of sad if you think about something like the Pythagorean theorem, I would argue. Now, the claim is, and that is the flexiformal approach or the flexiformal paradigm, is that formality does not need to be the strict binary, i.e. either something is fully formal or it's like entirely informal. It can be a spectrum if we want it to be. The way that that could work, for example, is to introduce formal islands in otherwise purely informal Cs. By, for example, just marking up certain words and letting them be associated with some unambiguous identifier somewhere that points to a semantic, more or less formal definition of the thing. So you could have some definition like for a group here where you just like reference the concepts that are being invoked by certain phrases by annotating them directly on the text. You can have otherwise fully formal expression that just have informal gaps in there, which still allows you to do things. So in this particular case, we could have this giant tensor product where there's this f in there and we don't actually know what it means. But we don't need to necessarily know what it means in order to, for example, just figure out that the result of that needs to be some kind of thing in some kind of vector space. Yeah. That is basically the claim of the flexiformal approach. And if we go that route, if we keep things flexible and like on a spectrum, then of course we keep lots of the nice things about informal mathematics, which is we can use natural language where adequate, we can keep all of our notations and terminology, we can omit details to the extent that we want to or find useful. We can keep things unspecified, we can deal with remarks, examples, exercises, and all of that. And of course, the more we do that, the more we lose useful features, like for example, full automated or interactive theorem proving, unless of course we go the fully formal route, at which point we like also inherit all of the drawbacks of formal mathematics. But staying on the spectrum basically allows us to select the point where we think the trade-off is the most worth it, or whatever our current application is. And my claim would be that, given that we have a standard format for informal mathematics already, or a standard system, we can do basically this also in LaTeX, and that is what STEC attempts to be and or do. So my claim would be that STEC allows for integrating semantic annotations in arbitrary LaTeX documents and covering the full flexiformal spectrum from fully informal to fully formal. Fully informal is easy, you just use LaTeX. Fully formal gets a bit more complicated. And then what can we do with that? We can generate active documents from that, which we can augment by semantically informed services. The entire pipeline consists of basically 3 pieces or 4 pieces of software, depending on how you count. The first thing is just the STEC package for LaTeX. That is on CTAN. You just write use package STEC and then you're good. And then you can write your things. And then you can generate PDF, and that of course gives you all of the limitations of what PDF can do. You will notice all of these blue words, that's because these slides are written in STEC, and so the best thing you can do in PDF is I can click on a thing and then it will jump to a definition somewhere if I were logged in, which apparently I'm not anymore, I don't know why. Well, if I were logged in, you would now see a definition. That's the best we can do in PDF. Alternatively, what you can do is you can run the Rustech software over the whole thing that will generate HTML. For that reason, we wrote our own text to HTML translator for convoluted reasons I probably don't necessarily have to go into. Which then preserves both the way that your document is actually supposed to look like and all of the semantic annotations. And if you have the semantic annotations in HTML, then you can throw JavaScript at it and let it do things, whatever that is you want it to do. We can also use the MMT system to then import that HTML, extract all of the semantic annotations, and serve as an additional semantically informed back-end to introduce more functionality into that JavaScript-oriented HTML. And since we're now at the point where we need 3 pieces of software, we introduce a 4th piece of software that integrates the other 3 so that you don't have to deal with that, which is a VS Code plugin, which you can install and that ideally does most of the work for you in the ideal case. Some foreshadowing on things I'm going to talk about later, which is where you can find all of the stuff that we've already done in STEC. The upper one being literally all content we have, including research papers, libraries of various concepts, all of these kinds of things, and our flagship product, basically, which is this Alea platform, which we use as a course portal for our university courses by now. Chances are you've seen that if you've talked to Michael at some point over the last couple of weeks, whether you want to or not. So to give you some brief overview of what that actually looks like, for those of you who are interested in, apparently I've been volunteered to give a workshop, which is a good idea for those of you who are interested, that we can actually show you these kinds of things and help you set things up, because this is research software with all of the usual problems associated with that. But the basic idea is that STEC allows you to more meaningfully declare semantic macros. For those of you who don't know, generally I think users of LaTeX come in 2 flavors. There's the ones who like literally write everything on a low level. So if you want to have substitution of variables in a formula, they're going to write a \wedge b open square bracket x/c whatever. That's the one camp. The better camp that I'm in are the ones who have a long assembled preamble with a couple of hundred new commands at the beginning, one of those being subst, for example, and then you just write \subst, and if you're annoyed with the notations, you can just change it. STEC is basically that on steroids. So instead of new command, you will write symdeco. That also gives you a semantic macro of that form. But in particular, it also generates a unique identifier for that thing. You can give it a name. You can then give it a bunch of notations from which you can pick at some point. And you can associate it with more various kinds of formal information like types, formal definientia, these kinds of things if you want to. We can then collect them in modules, which is the biggest pain point in the implementation of STEC, namely that we have to crowbar a module system into TEC, which is a lot of fun, but feasible, fortunately, which you can then import via use module or import module, depending on how you want to have modules behave down the line if you then re-export things. Yeah. And of course, that gives us the nice bonus objective that we can develop these kinds of libraries of concepts with their notations and potentially their formal aspects collaboratively to some extent. And the nice thing about that is that it allows you to separate concerns to some extent. If you're an STEC user and you know where your symbols are, you can just use them and you don't need to care about the formal details necessarily. The more you want things to be formal, the more difficult things get. That is just the side effect of formality. But the nice thing is that using them is easy and you can leave the formal stuff to the people who actually care or have the expertise to do that. And if there's stuff that doesn't exist in the library yet, you don't need to care about the formal details at all. You can just declare your symbol and then go ahead and use it. And then leave it to others to subsequently at some point add the formal details if they want to. Regarding the narrative stuff, I only understand 3 of those 4 boxes, which is why I'm going to ignore the one that is not blue. It has turned out that the way that is useful to think about these kinds of things is to see it as a separation between basically 2 models. There's the domain model, which contains all of the formal stuff. We have our symbols, we have our types, definientia, all of the notations, how they relate to each other, and these kinds of things. That is the stuff that is basically universal, independent of the authors, independent of the language of the authors, and that we can correspondingly share as wide as possible. And then there's the formulation model, which you're also able to share, but more importantly, you can customize that to however you want things to look like. Those are things like informal textual definitions of things in whatever language you speak and or want to speak, theorem statements in a readable manner in whatever natural language you want to use, theorems, examples, remarks, all of these things. They can use the domain model however they want, and you can share those, but you can also change those without having to introduce your own symbols from scratch every time again. So much about the formulation model and the domain model. I don't know what the rhetoric model is in contrast to the formulation model. The 4th thing that we can do in terms of services is to then have a learner model that keeps track of what you do when you interact with active documents to figure out what you already know, what you do not know, and to some extent tailor services to that. I can get to that later. We have a couple of use cases, the flagship one being the Alea system, which I mentioned earlier, our course portal. We have all of Michael's lecture notes up there, written in STEC and augmented by semantic features. That was part of a project called Volk.ai, where we basically figured, hey, we can use this as basically a way to get money to do interesting research things and then develop that on the side. It then turned out that that was way more fun and way more productive and way more useful in practice than we figured, with the result that most of my time and resources is now basically spent on that, rather than the things that in theory I'm technically more interested in. I.e. the result is that I'm currently a ridiculously overpaid software engineer with no formal training in software engineering. And I'm not necessarily complaining because I have a lot of fun, but it also means that on the lower side, where I think things are more interesting from a formal point of view, progress has a bit slowed down and is now to some extent starting to pick up again. Apart from this course portal, we have various research papers, which is a good basically sanity check that whatever we're doing actually works independent of our particular workflow with respect to MMT and all of these stuff. So we can write papers, we can put them on Overleaf, we can submit them on EasyChair with all of our semantic annotations, and that works still fine. With respect to formality, STEC is MMT complete. So for those of you who don't know, MMT is this quote-unquote formal system developed by Florian Rabe in our research group. The design of STEC is of course massively influenced by exactly that, but we managed to get it to the point where it is a feature-complete input language for the MMT system. And then with respect to other formal things, we have a few experiments ongoing, which hopefully will now soonishly pick up again. We can type check STEC content by MMT, and therefore, of course, also check proofs to some extent if you're willing to write them in the first place. We can do some amount of computation. We've experimented with integrating the LEO3 theorem prover into MMT and have like check STEC code using Leo. That has not worked, but not for like principal problems, but really just for system integration problems, the usual problems. If you've talked to Florian Rabe at some point, you know that he's currently working on this dependently higher order logic thing. I basically just took his formalization of that in MMT and ported that to STEC to see whether that works, and that worked surprisingly well. I can show you all of these things gladly, since I still have 10 minutes anyway. I'm very flexible depending on what you want to see. Some things to note with respect to future work that are relevant is to make the entire thing more stable, first and foremost. Those of you who've toyed around with that in the last few weeks might have hit a couple of pain points, which I'm very much working on getting rid of. And then there's a couple of actually interesting research questions, which is what features we actually need in STEC to conveniently represent mathematical content in some close to formal manner in the first place. We have a few ideas and we have more things to experiment with to figure out what that actually means. If we want to sneak in more formal more formality into STEC content, of course, the obvious question is what kind of foundation we might need to use for that. In general, the goal is to stay foundation independent and correspondingly pluralistic, but there probably needs to be some kind of default thing that people can just work in without having to bother with things. If you want to annotate actual natural language statements, then the syntax gets very convoluted very quickly and correspondingly difficult. I consider the current state of STEC for doing these kinds of things as the analog of whatever JavaScript is with respect to TypeScript. So the question here is actually, what do we need in terms of pure syntax to make things more convenient? And of course, the holy grail of the entire thing is to integrate existing software such that it becomes available to you from the point of view of just writing your STEC code in LaTeX. Yeah. And at this point, I can basically just show you things whatever you're interested in.
We have 10 more minutes.